Uh, yeah. Cool. Thanks, Dr. Peoples. How's everyone doing? Good. Okay. Very lively today. Yeah. So, Dr. Peoples said, I'm Connor McCurley. I'm a senior machine learning scientist at a small startup company called Orbital Sidekick, which I'll tell you more about today. I'm originally from just outside of Oklahoma City, so not that far from here. Definitely sympathize with the howdies. So, um, that's awesome. Moved around a lot, lived in Florida for a long time. My fiance just graduated from the University of Miami Law School, and I just moved to Philadelphia. So it's going to be below freezing when I get home. So I'm loving the weather right now. Um, so yeah, I know that the seminar last week was also about hyperspectral imaging. This one is not going to be that technical. Honestly, I'm going to kind of a broad overview about what hyperspectral imaging is, and then talk a little bit about the company I work for. And then very, very briefly, just talk about some of the trends we're seeing in Earth observation and some career advice. You all will be graduating soon. So is everyone in here a PhD student or master's? Yeah, okay, cool. So you understand the struggle. Yeah, so Orbital Sidekick is a remote sensing Earth observation company. So if you don't work in the space, what is remote sensing? The idea is that we're able to capture characteristics about the Earth without direct contact. And there's many different modalities that we use to do that, ranging from optical, LiDAR, and hyperspectral, which is what we use. And it gives us a way to monitor the Earth at a global scale with measurements that are repeatable. So there's many different reasons why you might want to do this, ranging from policy, informing policy, obviously different industry decisions, and just better understanding the Earth. So yeah, so there are many different really complex phenomenon that we might want to measure on the Earth, ranging from, mapping stressed vegetation, looking for greenhouse gas emissions that are invisible through normal optics, characterizing, um, you know, before and after a wildfire burn to learn how to better prevent that. And hyperspectral imaging is one modality that allows us to do these type of analysis. So essentially, a hyperspectral camera, what makes it different than normal RGB or other type of modality is that we are capturing electromagnetic energy across a really broad spectrum. So we're ranging from visible all the way through the short infrared. And what that allows us to do is when we image materials on the Earth, based on how that light is reflected or absorbed across this whole broad range of spectrum, it allows us to tell the chemical makeup of these materials. So we can actually, from space, distinguish between different materials. So you all have probably seen this before at some point in your life. This is just a chart of the whole electromagnetic spectrum. So it ranges from ultraviolet, visible, into the infrared, near infrared, midwave, long wave, and beyond. So hyperspectral is typically capturing between the visible all the way through the shortwave infrared. So a lot of spectral detail. And again, what makes it different from RGB? RGB looks at three specific wavelengths. So that's normally around like 460, 560, and 660 nanometers. You take an image filtered at those three wavelengths, stack them together, you get your RGB image. But sometimes the phenomenon we want to measure are at different wavelengths beyond that, right? So the next step would be to look at more wavelengths, usually up to 20. We call this multispectral, and that's good for certain things. But if we want more spectral detail, hyperspectral is where that fits in. So compared to 3 or 20 wavelengths, we're normally looking at like hundreds, like beyond 400. So you get a ton of spectral detail. So what this creates, compared to like a normal image, is that we get an image like this. We call it a data cube. So essentially every single pixel would have an associated latitude and longitude, and then another channel, which is all those spectral bands. So up to 400 or 500 spectral bands. And each pixel constitutes something that we call a spectrum. So a spectrum is essentially the measurement of how energy is interacting with the materials on Earth's surface. So electromagnetic radiation is emitted from the sun. It passes through the atmosphere, and then it interacts with materials on Earth's surface. And depending on the chemical makeup of those materials, some of that energy is absorbed and then some of it is reflected back. So the energy that's reflected back passes back through the atmosphere and up to our sensor in space. And yeah, so that interaction defines, we call that a spectrum or a spectra. And those are unique given different materials. So we're able to use that to do classification of different materials. So you can imagine if you only had like three colors, like an RGB image, and you were trying to distinguish something like asphalt against these grass or maple trees, like through an automated process, like we would look at these wavelengths down here, those would all look really similar to each other. So creating an automated way to do that with just spectral information would be really difficult. And you can imagine even with multispectral, we maybe have 20 measurements. Depending on where you sample these, like it might be really hard to distinguish grass versus maple tree, right? So like we would obviously be able to tell like vegetation versus non-vegetation, but if you actually want to be able to do that speciation, having all this spectral information is really useful. So ideally, in hyperspectral, the pixels are pure. So like every pixel that we have would only contain one specific material. But as we scale that up to satellite imaging, that's just never the case. Like any single pixel on Earth for hyperspectral is typically around 30 meters by 30 meters. So it's like a huge area. So one problem that we face is that these pixels are mixed. So you can imagine if we were trying to design a classification algorithm to detect trees, it wouldn't be as simple as looking at that pixel and saying, oh, there's a tree spectra there, because it's going to be mixed with other constituent materials. Like in this example, there would be grass and sand as well as the tree. So we often represent this as a linear mixture. So the radians that we would see would be some just like linear combination of all the constituent materials being tree, grass, and sand multiplied by their abundance. And abundance is basically just how much any particular material fills a pixel. So that's just one challenge that we have to work with as we scale up to satellite imaging. There are three typical systems for collecting hyperspectral data. The one that we use is the one in the middle. We call it a push broom. And so essentially, you collect one spectral line at a time, and you form your image through the satellite's motion. So I can show you a video here, if it'll load. So this is an example of our satellite going through its orbit path, and we're trying to collect data over the Golden Gate Bridge. So we collect one line at a time, and we form our image through the satellite's motion. So this entire green strip right here would end up being one collection that we could process. So one giant data cube. Yep, sorry. Yeah, so the typical processing pipeline, we collect data at the satellite. This is just a raw value. We call it a digital number. To make this useful, we have to calibrate the sensors. So we fly over, we task our satellites over different collection sites that are really well regulated. And we're able to map our digital numbers to actual units. So we have radiance. And in some tasks, like radiance is good enough. So I'll show you an example where we do greenhouse gas detection. There are reasons why you might want to do this in the radiance domain. But if you're trying to do like surface target detection, remember, all that energy is passed through the atmosphere twice. So to be able to characterize what a material looks like on Earth, we have to try to remove all the atmospheric effects, right? So the energy gets absorbed by water vapor and the air that goes through different scattering. So we perform a process called atmospheric correction. And the idea is that this will map the data to look like how it would if we were just to go and collect a signature right on top of the object on Earth. And once we do that process, we can look at producing different analytics like target detection, greenhouse gas detection, et cetera. So yeah. Between these two? Yeah, calibration. This one is infinitely harder for different reasons, which we can talk about later if you want. Yeah. The calibration, actually, like it's pretty well documented. You fly over these sites and you basically just find a correspondence between your data and the known radiance data at the site. So, okay, so there are many different applications for hyperspectral imaging, ranging from energy, agriculture, urban, obviously defense. And so at Orbital Sidekick, we kind of have our hand in all of these different business sectors. So who is Orbital Sidekick? We're a really small startup company. There's about 20, maybe 25 employees based out of the financial district in San Francisco. And our mission is to produce the most robust sensing and analytics capability available with a core focus on sustainability. Now, we're doing that by developing, launching, operating satellites in space with our own proprietary hyperspectral cameras on them. And then we provide analytics to various different customers, mostly focused in energy and mining, as well as the US and foreign governments. So kind of just to give you like a timeline of where we are, we're a pretty new company. We started back in 2018. Essentially, we developed our first hyperspectral camera, got it put up on the International Space Station. Once we showed that that was successful, we went on to launching our full integrated system. So that was called Aurora. That was back in 2021. So we have one satellite at that point floating around. It's successful. I started at the company in 2022. And then pretty soon after, we launched 3 satellites and then 2 more after that. And we currently have one sitting in storage that's like ready to go next quarter. So we'll have 7 satellites that are collecting data for us. And why have we been successful? Our hyperspectral cameras are honestly just really good. Like they're the best that you can get in the commercial sector. So we have a spatial resolution of about 8 meters. So every pixel on the ground is 8 meters by 8 meters. I'll show you in a second. That's like pretty unprecedented. To also have 468 spectral bands. So we have bands ranging from 400 nanometers all the way to 2500 nanometers. So just like tons of spectral detail and also really good spatial resolution for hyperspectral. Yeah, so whenever this is a map of like our competitors, you see like whenever you're designing a satellite, a hyperspectral satellite, you like there's normally like this linear correlation between what is your pixel size versus like how many spectral bands you can get. So there are definitely trade-offs, and it's like somehow we're way out here, which is just crazy. Yeah, so we're doing cool stuff. I'll show you an example of one of our satellites. So we build satellites. They're called CubeSats. So they're really small. So there's me. They're really small and they're relatively cheap for satellites. So the idea is that they are only going to be in orbit for about 3 to 5 years, which is actually a really short period of time. So it's kind of unfortunate because you have to continuously be putting up satellites to maintain your coverage. But it also allows you to put up new technological developments as they're made. So just as an example of how we launch these, so we partner with SpaceX. So this is a SpaceX launch containing 2 of our satellites. So this is the whole, you can see my mouse, the rocket, and then up top is where the payloads are actually stored. So our satellites are up in there. You see a launch. And there are 2 of our satellites floating around in space. So these are about to be ejected into orbit. I'll show you the next slide. So this is not the same video, but you can see where the satellite is being released. So this looks really slow in real time, but I'm telling you, like these guys are flying through space. So they essentially are just like free spinning like crazy fast. And then at some point you hope that you can gain control of them and they go along orbit. Yeah, and this is just an example of we've had 5 satellites collecting images over a 2-year period of time. This is essentially how much area we were able to cover. So our goal is to get up beyond 20 and hopefully get daily global coverage of the Earth with hyperspectral data. So Yeah, so we do a lot of work in different sectors, energy, mining, defense being the primary ones. I told you I'm a machine learning scientist. In the last 3 years, I've had the opportunity to work on a lot of really interesting projects, ranging from regular machine learning to classical detection theory. Some really interesting ones being early stage wildfire detection and characterization. We're building foundation models for hyperspectral data, all that kind of good stuff. But I thought I would kind of just briefly show you like three small uh, projects. I'm not going to get like into the technical details. Oh yeah, so just a little bit of math here. Um, if you know anything about machine learning, you know that when you have really good features, you don't need to use complicated models. So it turns out that it's actually really, really difficult to beat classical detection theory um, when we have really good spectral data. So kind of the primary algorithms that we use are called the match filter, the normalized match filter or ACE, and then the spectral angle mapper. And then most innovations are kind of built on these algorithms. So like the clutter tune match filter tries to mitigate false alarms. MIACE is really good when you don't necessarily know your target signature or you're working with mixed spectra. Um, but how do these algorithms work? So these are all detectors, essentially. So we have some observation X and then some spectra that we would know ahead of time. So we work with really large spectral libraries. Some are proprietary, some are open source. And essentially, you're just measuring the inner product between the observation and the target signature. So that's just a normalized dot product for the match filter, and then it's whitened by the statistics of the background. So essentially what we're trying to do is decorrelate our data from the background and then do the inner product comparing the angle between those, the observation and the known spectra. And then ACE, you can see, is pretty much the exact same thing, except in this case, we're also normalizing by the magnitude of the data. So there are different reasons why you might want to pick one detection statistic over the other. So spectral match filter, if you think about this just in terms of the spectra, um, spectral match filter looks at both the shape of the spectra and the magnitude of it. And so one example might be when we do this greenhouse gas detection. I'll show you that we need to know that magnitude information. On the other hand, if we're just doing surface target detection, you really just care about the shape of the spectra. Like the magnitude doesn't matter. So another classic algorithm is called SAM. Essentially, it's just the angle between the observation and the spectra. There's no whitening. So yeah, I'll go through three like quick examples of projects we've worked on. So one was essentially to do tracking of an oil spill off the coast of Singapore. This is something that is not well defined in hyperspectral imaging. So there was a big oil spill last summer, and then in about a 10-day period of time, most of it was cleaned up. And so we just kind of wanted to test like, hey, can our sensors track this oil over open water? So this is just the site for more information. So we hadn't done this before, so we needed to verify, did any of these algorithms work? So we got some verified data from Avarice, which is another hyperspectral sensor that the statistics of it are pretty similar to ours. And you can see down here, like this is open water. There's a really thick emulsion of oil right there. And then the top one is a sheen. So it's like a really thin layer of oil on top of the water. And we just compared those three algorithms that I just showed, the match filter, SAM, and ACE, and then also this custom band image that we made. So one of the really cool things about hyperspectral data is like there's a lot of physics tied into it. So you don't necessarily need to use the entire spectrum if you are familiar with the features that you're looking for. So one common one that you've probably heard about is called NDVI. It's like the normalized difference of vegetation. So essentially, if you're trying to classify vegetation through hyperspectral, like there's a crazy large red edge in vegetation regions. So you can just use like a ratio of that to help you classify that. So anyway, so we split all the data into these algorithms. Hey, look, all of them were able to find the oil, so that's great. Awesome. So as an example, so this is now our data. So here are some like RGB composite images over different periods of time. So at June 16th, we knew that there was oil in open water. You can see from the ACE detection map, like, hey, we can see the oil through the open water. That's pretty cool. By June 25th, most of it had been cleaned up or at least like contained during the shore or contained near the shore. And our detection map showed that all the oil was contained by the shore. And a few days later, most of it was pretty much cleaned up, maybe some remnants on the shore, and that's exactly what we were able to see. So this is one application where hyperspectral hasn't really been used before, but it's really promising. So being able to track oil spills, see how they flow into different waterways for environmental impact assessment. Yeah, really cool. Another primary example of where hyperspectral is used, for us at least, is in greenhouse gas detection. So oil and gas companies have us fly over their pipelines to basically look for methane leaks. So you see these like big plumes coming off their equipment. And how are we able to do that? So methane and other gases follow a rule called the Beer-Lambert law, which essentially is saying that the data that we're going to see is going to look like the background, right? Because this is an invisible gas. But the data that we'll see, if there's methane present, will be attenuated by this absorption profile and some concentration path length. And that concentration path length is essentially, the concentration and the length of the plume that the light has to go through. Yeah, so how does this help us, right? So knowing Beer-Lambert's law, we're able to construct our own hyperspectral signature for methane. Like, what would methane look like over our data? And we can plug it into ACE or the match filter. So it actually turns out, if you do some math, that concentration path length, which is basically telling you how much methane is present, is directly proportional to the output of the match filter. So just as like some examples of these detection maps that we get. So this one is in West Texas in the Permian Basin. So honestly, not that far from here. And this one is looks like Oman. So this one is like a giant plume. But we're able to see these with our data. So that is cool. And then the last really quick example is something that we call spectral fingerprinting. And so this is like the core technology of hyperspectral data. It says, hey, I'm looking for a specific material. I don't know where it is. Go find it. And so the challenge here is, how do you scale up this process to eventually be automated for global coverage? And so we use really large spectral libraries. And I'm not going to go through all the math here either, but show you just two quick examples. So the US government came to us with some materials that they were interested in finding. This one specifically was an ammonium compound that's used for fertilizer. So which is, on its own is not that big of an issue, but this specific compound is also used to make explosives. So we had a couple of different sites that we were interested in trying to look for this material. And we were able to find it over a couple different plants. And so this has never been done before, like not in hyperspectral, not in any kind of modality. If you were just looking at this through RGB, right? Like, how do you tell the difference between a white patch of gravel versus an explosive compound? So this was a really big win for us. And another example that has not been done from a satellite platform was the detection of oil spills on land. So if you look down in this Google Earth image, there is a location in Argentina that we were alerted to that was potentially spewing oil. So if you look at Google Math, like, there's clearly no oil to be seen with your naked eye. We were able to come up with some oil and sand spectral mixtures, basically task our satellites to look over that area, and we were able to find it. So you can see like our detection maps showed this region. And something that was really cool was that we were not only able to find the oil, which would have been invisible otherwise, we were also able to characterize its mixtures. So if you look like right in the center in that hotspot, that was classified as like a 2-to-1 oil to sand mixture. And then as it radiates out from the source, it went down to a 1-to-1 mixture, 0.5-to-1 mixture, and then eventually down to 0 where there wasn't any oil. So again, another really big win where like this technology hasn't existed before. So you can imagine for environmental monitoring, this might be really useful to be able to identify where large oil spills are happening, how are they affecting the environment around the area. We can compute other analytics to see how the vegetation is changing. And then obviously the oil and gas suppliers are interested because they're losing product and want to maintain the regulatory status. So, okay. So I know I don't, how much time do I have? Okay. We'll kind of fly through these. I had a lot more slides, but I didn't think I was going to have that much time. So some key trends that we're seeing in the Earth observation industry that is allowing us to grow. Essentially, things are getting a lot smaller and they're getting a lot cheaper. So obviously, it's more accessible for us to build things like these CubeSats. We're also seeing a really big transition from government to industry. So typically, satellite missions they would be run by government industries, and there are these huge satellites that are meant to be in orbit for like 20 plus years. But that's not what people want anymore. They want coverage, and they want a really fine temporal resolution. So a lot of this shift is moving towards industry where we're building things like these CubeSats where we can put up 20 of them for the same price as one big satellite, and we're able to get a lot more coverage. And that's helping us move towards more real-time analytics. We're also getting a lot better at multi-sensor integration, so combining different modalities. So, and it's become very clear that that's necessary. So as an example, we are working with an organization to do early stage wildfire detection and characterization. So basically, when a wildfire sparks up, say we're in California, they want to know the second that it ignites. And they want to be able to assess where is it going to move. What did the area look like before the fire? What did it look like after the fire? And with our data alone, that's just not possible. Like our swath width is too small. The downlink time is too long. So we're able to partner with another satellite company who does thermal infrared imaging. And instead of having a low Earth orbit satellite, theirs is way out into space where it's basically stationary. So instead of the satellite orbiting the Earth is basically turning while their satellite is in place. And they have so their pixel size is really, really big, but their sensitivity is really high. So they can detect that heat pretty much as soon as it sparks. And then that informs us to go task our satellites over that area to perform a characterization. So being able to have partnerships where we're combining multiple different modalities, we're definitely moving in that direction. And then challenges, a lot of challenges. So I don't know, how many of you are maybe working in machine learning or in Earth observation or, okay, like one guy, okay. Some things to think about if you ever work with remote sensing data. Data volume is a huge issue. Every single scene that we collect is about 10 gigabytes. We collect, let's say, 300 scenes, each at 10 gigabytes in a single pass. And we have about 15 passes a day. So we're talking like petabytes of data that we're storing in a pretty short period of time. So how do you work with that volume of data? How do you store it? How do you access it in an efficient manner? These are all things that we have to consider. And if you're developing models, annotation uncertainty and annotation scarcity, all right, sometimes you can't get accurate annotations because your sensor resolution is too small. I'm sorry, it's too large. So like as that example where I showed you with the tree where things were mixed, like you're never going to have a pixel level annotation for that. How do you deal with that? When you're developing your data sets, right? How do you make sure that the model generalizes to the entire globe? How do you make sure it generalizes across time? Is your data coupled temporally or is it coupled geographically? Like these are all challenges that make it really unique from traditional data sets. But that makes it really difficult. And then the actual modeling of this data, people have relied on a technique it's called lift and shift. It's basically where they take models that have been trained on traditional imaging data sets. So you might have a giant, Pascal VOC or COCO or these like traditional image processing data sets that are you'll pre-train a model and they will try to take that model and just fine tune it on the data. And oftentimes that doesn't work. Like it's better just to train from scratch. I don't know. I guess I'm just rambling now, but yeah, a lot of challenges. So a lot of really interesting things to look into if you kind of go down this direction. And then, yeah, I wanted to give you some career insights. I think I blocked out a bunch of these slides, but I'll kind of give you my path. Everyone's path is different. So I started off at a school, a really small engineering school in Missouri. While I was there, my dad passed away, so I moved closer to home, finished up my degree at Oklahoma State, and honestly, I had no idea what I wanted to do. Like I'd done a couple internships at an electric utility. I thought that's what I was going to do. Had a professor that basically said, if you go to grad school, they'll probably pay for it. So I said, okay, that sounds good. Didn't really even know what I wanted to do in grad school. Kind of just fell in and found my advisor. Met a couple other people who were going to be in the lab, like Dr. Peoples, and I was like, yeah, this sounds good. So not as much of a goal as I would have liked, but things worked out. And as you get ready to graduate and are looking for positions, some of you might know, like, hey, I'm definitely going to go down the academic route. You might say, hey, I'm absolutely done. One piece of advice that I was given that I absolutely hated at the time, but I think is really relevant is like, you don't have to find the perfect job when you graduate, okay? And you're not going to. There is no such thing as a perfect job, whether you go into academia, whether you go into industry. There's going to be things that you like and there's going to be things that you don't like. And as long as the things that you like outweigh the things that you don't like, you're in a really good spot. And I think you can have a really good career. So don't stress about it. Things are going to work out. How many of you are going to graduate like this semester? Anyone? Okay. Do you have a job lined up? No. Okay. Don't stress. Yeah, so I had a bunch of slides too about like the pros and cons of academia versus industry. I'm not going to show any of those, but if I could leave you with some advice, these are the core three things that I would really focus on. So one is your technical depth. Like you obviously know your research. Whether or not you're going into academia or industry, you need to be able to show that you know what you're talking about. So if you go into industry, you're going to have to do coding interviews. You're probably going to have to do a lot of them. They suck. You just have to do it. It's just the way it is. And if you go into academia, obviously you probably know your stuff. But you really need to focus on communicating. So when you leave this program, are going to know more about your specific research than probably any single person in the world. You're going to go work at another university or you're going to go work in industry. You're going to know more, right? I guarantee that no one cares really about technical details. So what you hate to hear, like you work so hard, you develop your models, you do all the math. No one wants to hear about it. You need to learn how to tell a story, tell why what you're doing matters so that you can sell it to people. And this is going to be important whether or not you're pitching this to your boss, whether or not you're writing a research proposal, like just learn how to be convincing, learn how to promote yourself. And then obviously everyone says collaboration, learn how to work across teams. So my last word of advice, be flexible. Like I promise it's really not that deep. I know things when you're in the thick of it, seem really, it's like the end of the world if you don't get a specific job or into a specific university after this. But be open. Like if you are flexible, you're going to be given a lot of opportunities in your life. And you'll have the opportunity to do a lot of really interesting things. So I think that's all I had because I skipped over a bunch of slides, but yeah, if there are any questions, I would love to answer them. I know I kind of rushed through all of that, so yeah. 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 Yes.
So I just want to clarify what you said, that you're talking about like physics-based algorithms.
Physics-based. Yeah. Yeah, I mean, it depends what you classify as machine learning. Like you could argue that a match filter is machine learning, but when you have good data that matches good ground truth, like we have these giant spectral libraries, which essentially would be the same thing as someone going right up to a material and taking a measurement. That's like the gold standard. When you have data that matches that really well, you don't need complicated models. So, yeah. Okay. Yeah.
You have any like that reference like that? I think that's very
I don't know that I have any papers referencing that. I think it's just kind of just one of those things that's known in machine learning. Like usually the simplest solution is the best. And it's like good feature engineering is usually more important than good modeling. I have a lot of papers that I could share with you in terms of like specific towards hyperspectral, but I would have to dig into that. But yeah, if you're interested though, like let's connect and we can chat about it.